Yeah, so I took, personal story, I took physics at a community college because when I was a teenager, I wanted to mow lawns for a living. So I had a truck and trailer and about 10 lawns. And then I was still living in my parents' house, of course. And my dad was like, well, they never discouraged me from it, but he was just like, if you want to, do that, you have two choices. You can either go to school or you can pay rent. And I was like, it's easier to go to school. So local community college had like an electronics program, so I went and started that. I was trying to choose electrical because electrical only had one English course, whereas electronics required two. So I was like, don't like that. Two more English courses, that sounds horrible. But the electronics coordinator pushed me into electronics because I had like a good score on some math placement test or something. So I actually transferred my second English course back to the community college after I transferred to NC State. So I had to take you guys have to take technical writing, right?
We do technical communications.
Technical communications. I had that course at some point, which was ridiculous. And it was ridiculous because like a graduate English student can't tell you how to make like a technical math. They cannot give you useful insight about how to write a technical document in a discipline, in a field which they're not in. Like it's a kind of a ridiculous situation. That really should be a course that's like taught by engineering, honestly.
Is it not? I thought it was.
Is it? Maybe it is here. Maybe it is here. Is it?
Engineering based.
That's wonderful if it is. That's fantastic. That's good. I felt sorry for that English grad student who had to teach that course. I'm like, it's so awkward. But anyway, I transferred that course back to the community college to finish my degree. So in the end, I only took one English course at the community college. Actually, that's not even true. I took it at a different course. But anyway, my point to all this was I took college algebra-based physics, like the 201, 202 course. I took that first as like in community college. And I loved that course because like the guy who taught it he just would tell a story really, really well. And much better than me, for sure. And his examples seemed very interesting to me. But there was no calculus in that course, right? So then I learned calculus that year, and then I ended up taking the calculus-based physics at Appalachian State University, which was like also kind of close to my house in North Carolina where I lived. But so in the morning, I would drive to Appalachian, take courses there, and the nighttime I would drive back to the community college and take courses there. One semester I was registered for 30 hours. You can register for 30 hours if you do it at 2 universities. They don't know about it. It's true. The courses at the community college are pretty easy though, so it's not as impressive as it sounds really. And but one of the courses I was taking that semester was Physics 2. I actually took like the university-based, like the calculus-based Physics 2. I took first. I took it before I took the the first, like the course you guys had last semester, 231. It's like I took 232 first and then 231 second. So it was like my physics education is really weird. But anyway, I don't know what that had to do with what you're talking about, but I'm sorry. I probably should go start the video again, but I'll just leave it. Sorry for the horrible noise I just made with the mic. But I'm not going to edit that, right? I guess I should pray. Dear Father, we just thank you for this time we have to meet together, and I just pray that you be glorified what we do, that we'd understand a little bit more about Gauss's law today, Lord. In your name I pray that, Jesus. Amen. All right, let me work something really simple to start with. This is exercise 22.1. Got to start somewhere, right? I don't think this is even Gauss's law. This is like, before that. And so it's like a flat sheet of paper, which I'll draw like that, all right? And it has an area of 0.320 meters squared. It's oriented so that the normal of the sheet is at an angle of 64 degrees to a uniform electric field. All right, so like, here's the electric field, right? Here's the normal to the sheet. And this angle here is 64 degrees, we're told, all right? And the electric field has magnitude 12 newtons per coulomb. All right. A, find the magnitude of the electric flux through the sheet. All right. And then part B says, does the answer to part A depend on the shape of the sheet? Why or why not? C, for the angle phi between the normal of the sheet and the electric field, is the magnitude of the flux through the sheet largest and smallest? All right, great. I will explain A, B, and C as we go on here. So let's do A. So A is pretty straightforward, right? The flux, in this case, this is like the most kind of simple case. It's the, so we just need to find the part of the flux which is this way, right? So if we do the electric field times A times the cosine of 64 degrees, that should give me the flux.
That'd be the energy field going in the normal direction.
Yeah, right. So exactly. So the electric field's got two pieces, right? It's got like the parallel piece and the perpendicular piece. And the perpendicular piece is the part that gives us flux. And because of how the angle's given, it's given between the normal, right? The other way you might give an angle is like off the surface.
Yeah, could you do like 90 minus 64 and then use that for the angle?
But then we'd have to use sine.
Yeah.
Yeah. Mm-hmm. So if I was given the angle up off the surface rather than from the normal, like the angle of inclination, so to speak, then I'd use sine here. But geometry is like this is, I can move these over to here and put that up here. So like cosine gives me the perpendicular piece. Okay. Anyway, so what we got? We got 12 times 0.320 meters squared times the cosine of 64. That was, I lost my newtons per coulomb. I'll put them out here so that they're not entirely lost. And what's that give us? Oh man, did I not bring in I think I have two calculators in my office, but neither of them are here. I guess it's up to you guys.
I got 1.68.
1.68 newtons per coulomb. All right. Oh, wait a minute. That's not it. It's 1.8 newtons per coulomb times what? And so it's actually Newton meter squared per coulomb, right? So that's the unit of flux.
Okay.
Whatever that's called. I don't have a name for it. I think there is a name for like the magnetic flux later. If I remember right, it's like a Weber or something, but I don't know if there's a name for electric flux. I don't remember one anyway. Now we can check this answer because this is an odd problem. So we look in the back of the book here, right? Let's find out if you punch the calculator buttons correctly. So we're looking for 22, chapter 22, exercise 22.1. It says 1.7 Newton meters squared per coulomb. So yeah, cool.
So why again is it the perpendicular one?
So like, here's like another example, right? If I had the electric field was like suppose the electric field looks like this, right? And it's uniform. And I was told, oh, this angle here, is, let's say theta, right? Then I could break down that, I could break this electric field into two pieces, right? There's like a piece that goes like this parallel to the plane. And then there's another piece which goes perpendicular to the plane. Right? And this is a right triangle. So this, of course, the magnitude of the electric field. To get the perpendicular piece for that angle, I would do E times the sine, right, of theta because it's the opposite angle. But if the situation is such that I'm given, this is my electric field, right, and the normal to the plane is over here, and I'm given this angle, which I maybe call beta, the trigonometry is not the same. See, because over here, like I have this is my perpendicular piece, and then this is my parallel piece of the electric field. And so the perpendicular piece in that scenario would be E times the cosine of beta. See, because the angle, here the angle's off the normal, whereas that would be the angle up off the plane itself, yeah. But the textbook tells us that the 64 degrees is off the normal to the plane, which is why I drew the picture like I did. Does that make sense?
Yeah.
Okay. The question B was, part B was like, does the shape matter? The answer is yeah. Oh, wait a minute. I'm not understanding the question correctly. They say no. So what they mean is like, what they're saying is, suppose the shape was like,
As long as it has the same area.
but this is all in the same plane. Like it's a subset of plane, right? And like the electric field is however it is, right? 64 degrees. So yeah, same area. That was the meaning. I was thinking, see, what I thought when I read that question was, I thought here's the plane, right? The electric field's like this. So the electric field stays the same. What if we do this? Well, then, yeah, it matters a lot. Like the flux through this, if I just consider the top of the paper, the flux would be 0 because I think whatever comes in here goes out there. So like I think if I bent the page into a cylinder, the flux would be 0 if I take the outward pointing normal. But that's not what they're saying. They're saying for a flat sheet of paper, what if you like made the rectangle different, right? Like if you, instead of doing a normal sheet of paper, you did like a longer but skinnier sheet of paper or something. Yeah, anyway. So the answer is no, because it's the same thing. Like it's still the area times the magnitude of the electric field gives us the flux. Yeah. And then C was the question for C is like, so suppose you have the choice of modifying the angle through which the electric field cuts through the page. What angle relative to the normal maximizes, what angle minimizes the flux of the electric field? So you guys tell me that. Like if I could do what? If I put 64 down to what? If I make it 0, then the electric field is like parallel to the normal. So then we just get E times A, right? If we make the angle 90 degrees, then the flux is 0 because the electric field's tangential to the surface. It doesn't give us any flux.
Can you have negative flux?
Oh yeah. Oh, you're right. Maybe I should say that the angle being 180 degrees would be the largest negative.
Okay.
But in terms of magnitude of the flux, 90 degrees makes it as small as positive. But you're right. The electric field, if it was pointing opposite the direction of the normal, that would give us negative flux. And 180 degrees would give us the largest negative flux. That's true.
And the flux is equal to the Gauss's law, which is Q included over epsilon naught, right? Or is it something else?
Yes, the Gauss's law says that the charge enclosed by some surface is equal to, divided by epsilon naught, is equal to the flux through that surface.
Okay.
Yeah.
Okay.
Let's see here if I can find it. So if there's a particular question you guys want me to work, let me know, but I'm going to try to find another one. So this one's kind of like, this one's kind of, it's not really, I want something, I'm looking for something, I found what I wanted, but it's an even problem, so I don't want to do that one. All right, fine, I'll do the even one. This is 22.6. So these problems really, they're just a warm-up to better understand flux before we do Gauss's law, but we'll start doing Gauss's law problems right after this. So this is a cube of side length L equals to 10.0 centimeters, all right? And the electric field is uniform, and the electric field has a magnitude of 4 times 10 to the third newtons per coulomb. And it says it's parallel to XY plane at angle of 53.1 degrees measured from positive x-axis. And then the question is, what's the electric flux through each of the 6 faces, S1, S2, S3, S4, S5, and X6? And what's the total electric flux through all the faces of the cube? So let me draw a little picture here. So here is X, Y, Z, right? And we're told that the electric field is parallel to the, it's parallel to the XY plane and 53.1 degrees. So that means it's something like this. If I drew it like this, so here's the electric field. Oh man, I'll get it eventually.
How do you know it's from, actually, I was going to ask, how do you know it's from the x-axis?
Yeah, well, it's just given. So this angle here is 53.1 degrees. And it's like that everywhere. I mean, I can't draw it. This picture doesn't do it justice, right? Let me just write down the formula for the electric field, because I feel like that eliminates the ambiguity here. All right, so it is the magnitude, 4 times 10 to the third newtons per coulomb, all right? And then times the unit vector that points in the direction of E. So can you guys tell me what the unit vector would be? That, like if I want a unit vector that points like this, right? This is X, this is Y. So what do we put here? What do we put there? I'll do the easy part. 0. See, because the Z, it's parallel to the XY plane, right? So it's a horizontal vector field. There's no vertical part to it, yeah? And apparently it should have positive components, right? So what do you do? Just, I think we just do what? Cosine of 53.1 for the X component? And sine of 53.1 for the Y component, like that would give me the unit vector that points in the direction of the electric field. Yeah? Let's see here. I'll let you guys tell me what that works out to. What do we got here?
The sine of
Like, what are these numbers? Like, what's 4,000 times the cosine of 53.1?
I'm going to do the y first, because I already have that.
That's fine.
I got 3,198.74.
I'll take your, I make it 0.7 there. And that's, of course, newtons per coulomb. And then we've got 0, right? Cool. So that'll be super, that's nice to have, because now we can easily calculate the flux through the other faces. Let me show you how to do it carefully.
But you already know that the top and bottom face has 0.
Very, very good.
It's parallel.
That's right.
Okay.
You are correct. Let me show you how to calculate that. So the rectangle, the cube in question, looks something like this, right? And it, in the book, they put the origin at the back corner of it, I think. So let me tell you how they're labeled. we have S1 in the back there, S2 is on the top, S3 is over here, and S5 is the front. Underneath, you got your S4, and where's S? Oh, the back. In the back. S6 in the back. All right, so I'm going to add some coordinates here. This is Z, this is X, this is Y. All right, and that's figure 22.6 in the textbook, okay? So, like the area for the first face, we could say is L squared. If we want to write it as a vector, the area vector, L squared, and the normal here is minus, 0, minus 1, 0, okay? A2 is L squared times the normal for the second one is what? Like the normal would be what? 0, 0, 1, right, exactly, like that, yeah. So 0, 0, 1. And the normal for the third would be L squared, A times what? 0, oh, yep, 0, what, 1, 0, right? And the area vector for the fourth one, so an area vector by definition is going to be like the area times a unit vector that points in the normal direction. So like the magnitude of the area vector is the area of the plane, and that's how we would define area vector. But so A4 is what? L squared times what?
0,
0, 0, negative 1. I'll allow it. Very good. And I guess I can write down here. A5 is L squared times 0, 0, minus 0, 0. Wait a minute. Oh, S5 is this face, right? So it's this guy.
Yeah.
Sorry. It's what? It's 1, 0, 0, right? And finally, A6, the sixth one is L squared times, we say negative 1, 0, 0? It's the back face, yeah. So then the flux through the first face is just equal to like E dot A1 and so forth and so on. Let me raise it up a bit because I have trouble writing too low. If A1 is E dot A1, the second flux is E dot A2, the third flux E dot A3, fourth flux is E dot A4, the fifth flux is E dot A5, the sixth flux. Now two of these, as you pointed already, are 0, right?
Which you can tell because of the unit vector times that would be 0.
Right, right. So like, yeah. So let's see here. So A2 and A4 both have only non-zero in the z component, and so when you take the dot product with E, you get 0. But geometrically, that was obvious to you from the start, which is great because those are, the electric field is tangential to those faces, right? It doesn't cut through it at all. And how about A1?
A1 would just be negative 3.
Yeah, minus 3,198.7 newtons per coulomb times L squared, right?
Yeah.
And what's the flux through 3?
3 would be the same thing but positive.
Okay, so 3,198.7 newtons per coulombs times L squared. The flux through 5?
Flux through 5 would be 2,401 times L squared.
Same thing but negative. So what's the, so there we go. Now we found the flux through each face, right? Yay. And of course, to finish the calculation, we just need to multiply by like 100, right? Because it was, no, not 100. We should work in units of meters. If we've got newtons, we don't want to mix newtons with centimeters, right? Because newton is a kilogram meter per second squared. So to keep the units consistent, we should really change the 10 centimeters to what?
0.1 meters.
Yeah, 0.1 meters, right? So like if I was to actually work this out, I would basically have 31.987 Newton meters squared per coulomb, all right? 31.98 Newton meters. Down here, 24.017 Newton meters squared per coulomb. And so we have, but the larger point is that the field lines do what? They come, where's the first face?
The X.
So they come into the first face, right? Because like the electric field lines, they're coming into the first face, and by the same token, they're going out of the third face. So we get a positive flux for 3, but a negative flux for 1. And likewise, we get a negative flux for the back face because they're coming in there, and we get a positive flux for the fifth one because they're going out there.
So the flux of the
In is negative, out is positive.
hole would just be 0?
Right.
Okay.
Yep. That is true. So what's the charge enclosed in this cube?
So 0?
0.
Because that's
Right. Yeah. So we add these together, the net flux through the whole cube is 0, and that's equal to the charge enclosed divided by epsilon naught. So therefore, the charge enclosed in this cube would be 0. So to get charge enclosed from something, we need the electric field to be like diverging from some point inside it. If the electric field is just flowing through a region, there's no charge there. It's just, yeah. Is this good? Okay. All right, let's try a Gauss law problem.
Is there any time there is like a 3D object that has a electric field flowing like in a straight direction through it where it doesn't equal 0, the net flux? Like if
I'm sorry, I'm say your question again, let me process, I'm sorry.
So, is there any way that the net flux doesn't equal 0 over a 3D object if, actually, yeah, that if the electric field is going in a straight path?
No.
It'll always be 0.
It'll always be 0. Yeah.
An opposite side.
It'll always be 0. Right, yeah, yeah. And can I erase? Okay. Let me just check something. Because if the stupid camera like doesn't get the bottom of the, I think it got it. I think we're okay. All right, yeah, we got it. I'll go over here next. So are you currently in Calc 3, or like what's the situation math-wise for you guys?
I took Calc 3 last semester.
Oh, okay.
But this, like, I understood everything up until like partial integrals and like partial derivatives. But after that,
But you saw it, so I'm allowed to make this comment. You're in Calc 3 now? Okay. Which is allowed, right? That's a co-requisite. But so you're saying, what if the electric field is constant?
Yeah.
So at the end of Calculus 3, we learned something called the divergence theorem. The divergence theorem says that the integral over a like a surface, I usually use the notation like boundary of a volume. So the electric field dot dA. All right. Well, that's equal to the, and this is like a double integral essentially. It's equal to the triple integral over the volume of the divergence of the electric field dV. So this is like the divergence theorem in Calculus 3. You'll learn this at the end of the course. The point is, if the electric field is constant, if E is just equal to a constant E naught, then like the divergence of the electric field is defined to be like partial E1 partial X plus partial E2 partial Y plus partial E3 partial Z. Well, that's manifestly zero if it's a constant electric field. So therefore, this is zero, but this is the definition of flux, that's what this is, right? So yeah, if the vector field is constant, then yeah, the flux through any closed surface will be zero. But we don't need calculus 3 to see that, right? If you just think about any closed shape,
It'll have an opposite side.
right, at whatever,
Go out.
exactly. If it's a constant electric field, one goes inside, it has to go out the other side
Yeah, okay.
somewhere. But this is how to prove it. Yeah. Okay, so I like Calc 3. All right, I shut up. 22.9 is maybe a good problem for us. Let's try this one. It's got 2 dots though. I don't know, 2 dots, you guys. 2 dots, are we ready? Are we awake enough for a 2 dot problem? So here's the deal. A charged paint is spread in a very uniform layer over a surface of a plastic sphere of diameter 20 centimeters. Like so. And so the diameter of this thing is 20 centimeters, and it's, we have Q minus 14.0 mu C. Mu is for micro, right? That's 10 to the minus 6. That's the multiplier. And great. So we've got this is...
Is it 20 centimeters the radius or the diameter?
Oh, it's the diameter. Thank you. 10 centimeter radius, right? I'll call that R. R equals to 10 centimeters, also known as 0.1 meters. All right. And we're told that this is spread uniformly, right? Spread uniformly. And then we're supposed to find the electric field A just inside the paint layer, and then B just outside the paint layer, and then C 5 centimeters outside the surface of the paint layer. Right, so we're supposed to find the electric field like here, and then just outside, so like right here, and then 5 centimeters outside the surface paint layer, so that would be up here, right? And this distance would be 5 centimeters. So there's a B, a C, right? So I'm just going to draw it like 2-dimensionally, because like trying to draw 3-dimensional, I don't think we get much. So, but of course it is a sphere, right? It's 3-dimensional. But if you were to imagine a Gaussian sphere like here, right? Inside there, it's a sphere, right? Are we told about any other charge? No. So we're supposed to assume that all of the charge is on the surface of the sphere, of the plastic sphere, as we're told, right? So if I look at this sphere, I've got the charge enclosed divided by epsilon naught is equal to 0. But by the symmetry, it's also equal to the electric field times 4 pi r squared. So therefore, the electric field is equal to 0 inside.
How do you know that it's equal to 0?
By this argument. Gauss's law.
How do you know that the charge inside is included?
It's a plastic sphere, and we're told that the charge is on the surface of the sphere in the problem statement.
Okay, so none of it on
Right.
the inside.
Now, if we were to talk about a uniform, like a solid plastic sphere, where the charge had been uniformly distributed, then we'd be back to that example I did like Wednesday. But that's not this. This is a surface charge. Yeah. Sphere is an unfortunate word, see, because we use sphere both for spherical shell and for solid sphere in here. So if you're ever confused about which I'm talking about, ask me. That is completely within your rights to ask. I try to make it clear in my problem statements, but you know, I will fail at some point in communicating that. Now what happens if we're just outside the sphere? Right? Just outside. Like here. So we can make a Gaussian sphere that encircles the thing, right? Now what's the charge enclosed in this case? Well, it's the whole thing, right? It's just Q divided by epsilon naught, and that's equal to the magnitude electric field, right? In case B times 4 pi. What's the radius? Well, the radius is right here. We're at R, right? So we do 4 pi big R squared. So my electric field at the surface, which I'm calling case B, we would just get, you know, like Q over 4 pi epsilon naught R squared. Now, of course, that's 9 times 10 to the 9th times my minus 14 times 10 to the minus 6 divided by 0.1 squared newtons per coulomb. And to be fussy, I'm just talking about magnitude. So like, skip the minus here, right? Skip the minus.
The 4 pi r squared.
Well, I guess the minus here. Skip the minus. Yeah.
The 4 pi r squared. That's the formula for the surface area of a circle, of a sphere.
Yes.
Okay.
Right. Because the magnitude times the area gives me the flux. Yeah. So I don't really put, I'm just talking about the magnitude, but the minus is indicative of the fact, well, if it's a negative charge, right? Which means the electric field points what? Like if I draw the electric field lines, what do they look like?
They'll point out.
Opposite of that.
Oh.
So remember the field lines go towards the negative charge.
Oh, yeah.
So like the electric field lines are going in, that's why there's a minus. Anyway, I need to do that calculation, whatever that works out to. I have no calculator. Just a second, I'm gonna fire up the Wolfram Alpha. I encourage you guys to use Wolfram Alpha for calculating things in here. Oh, you got one? No, I can't use that. Sorry. It's just I'm not good with that. That particular model of calculator, it's okay. I just need to fire up the. I like Wolfram Alpha. When I'm working out your homework problems, like it's the first time I've worked one out, and like haven't worked it out before, I usually use Wolfram Alpha to like check my numerics. You know what Wolfram Alpha is? You know what I'm talking about?
I think it's a physics, like graphing thing.
Let me show you guys. You guys don't know what Wolfram Alpha is? Really? Oh, okay, cool. Well, let me show you. You haven't lived. Let's see here. So, aw man. Well, 9. Do you guys know where the 9 times 10 to the 9th came from? Do you know what I did there?
The 4 pi.
Yeah, 1 over 4 pi epsilon is essentially 9 times 10 to the 9th. To be fussy, it's 8.99 if that's bothering you. That's the K, yeah. So 1 over 4 pi epsilon naught is equal to essentially 9 times 10 to the 9th. Nine times 10 to the 9th, and then we had times what? 1.4 times...
Negative, oh wait, it would just be 14 times 10 to the 6.
1.4 times 10 to the minus 6. Was it 14 or was it 1.4?
14.
Oh, okay. Fix that. And then that was all divided by 0.1 quantity squared. And beep boop bop boop. So if I haven't messed something up,
So the
9 times 10 to the 9th, 14 times 10 to the minus 6 divided by 0.1 squared. Yeah, so we get 1, 2, 3, 4, 5, 6. So 1.26 times 10 to the 7th. 1.26 times 10 to the 7th. Newtons per coulomb. But you guys never seen Wolfram alpha before?
It looks like it's just.
Oh, it's wonderful for checking your work. Check it out, right? Like, I don't know. What's like partial derivative of the square root of x squared plus y squared with respect to x. There it is. So like you can write out math things in words and it will interpret it. It has some AI. But also, like, suppose you want to know what's the exchange rate with Finland? Oh, come on. Oh, they do euros? Well, that's lame. So apparently, 1 euro is 1.11 US dollars at the moment. Or how about this? 100 US dollars in yen. There you go. 14,539 Japanese yen is $100. It like updates this kind of stuff daily. There's all kinds of like real world data built into Wolfram Alpha. I don't know where it gets this stuff, but it. And then you can do other stuff if you want, like. Anyway, I digress. So that was B, and then for part C, what would we do? We have what? We have for part C, it's the same. It's the same as this, right? It's still 9 times 10 to the 9th times the 14 times 10 to the minus 6th, right? But now instead of dividing by 0.1, we divide by 0.6 squared, right? Why is that? This is very poor planning on my part, but if you can get someone back up there.
Because it's.
Oops. Yeah.
Wait, wouldn't it be 0.15?
What problem were we doing? Which one was it? 22.9? 22.9. So the sphere was 20 centimeters in diameter, 10 centimeters, and then 5 centimeters. Oh, yes, you're right. So not 0.6, but what? 0.15. Yeah, thank you. 0.15. Yeah, we would have figured that out when we checked our answer, right? So look, the sweet thing about using Wolfram Alpha is even if you mess up and do something like all this nonsense, you can go back to where you were because your browser has a history, and you go 5, and then bam, answer 5.6 times 10 to the 6th. Newtons per coulombs. Or if you like, 5.6 meganewtons per coulomb. All right. Mega is 10 to the 6th. So like Mega Millions is false advertising because it's not actually that much money, right? I don't know. I don't play the lottery. Some do, but I'm not against it. I just forget to. I think it's about as reasonable as getting insurance. At least it's optimistic, you know? Oh, we should check our answer. 22.9, right? So I can check the answer. and it's got 0, and then it's got 1.26 times 10 to the 7th newtons per coulombs radially inward, and then 5.59 times 10, did I say 10 to the 6th? I meant 10 to the 7th. 1.26 times 10 to the 7th newtons per coulomb radially inward, and then 5.59, 10 to the 6th newtons per coulomb radially inward. So they're both radially inward. I forgot to say that. So you guys have any questions before I go on, or no? All right.
So if it's a shell, wait. Yeah, if it's a shell, then it would be 0. But if it was had volume.
Yeah, if it had been
It was a sphere.
if it was a solid charge, then the electric field would have depended on.
It would be a ratio of the big circle to the smaller circle.
It would depend linearly on the distance from the center of the sphere.
Yeah.
Being 0 at the center and then linearly increasing to this value at the edge. So. Let's see here. Let's try to do number 41. That one's kind of like what we did today in class, so that might be good. Yeah, Wolfram Alpha is pretty good for, it'll do a lot of things like series, like if you want to calculate a series numerically, it'll do that if you just use your words. It'll do a lot of things. It is not without flaws, like it can be tricked, but it's relatively hard to do that. So this is number 42. Oh no, I want to do 41. 22.41. This is a problem. 22.41. And here's what it says. A solid conducting sphere with radius r that carries a positive charge q is concentric. So let me start out here. We've got a solid conducting sphere. It's got radius r. Charge q. All right, it's a solid conducting sphere. Is concentric with a very thin insulating shell of radius 2r. So out here, we've got a thin shell. All right. And we're told that out here, this guy also has a charge q on it. Thin, insulating, has charge. Q as well. All right. And the charge Q is uniformly distributed over the insulating shell. Then we're asked to find the electric field, magnitude, and direction in each of the regions. 0 less than R, 0 less than R less than R, R less than R less than 2R, and then of course R greater than 2R. We will not need Wolfram Alpha for this part. Okay. Put this over here. Put this over here. All right. So what did we learn about, this is a conducting sphere, right? We're told that in the problem. So what did I share with you guys today? The conducting sphere does what? All of the charge is on the edge, right? So that Q is actually smeared out uniformly like this.
So would the first one just be 0 then?
Yes.
Okay. Because it's inside.
Right. So exactly. So if I was to take my, Gaussian sphere of radius r here in case A, And let me call this case A, B, C for the sake of discussion. So in case A, if I look at Q enclosed divided by epsilon naught, it's equal to 0, right? And that's 4 pi r squared times the electric field. Tells me the electric field inside is 0. Which I told you guys today, like inside a solid conductor, the electric field is 0 in the electrostatic case. Maybe also interesting to think about, what is the charge density? Like how much charge per unit area on the surface here? This is not asked by the question, but while we're at it, let's let me just throw it out there. This guy has sigma equal to Q over 4 pi r squared. Like that would be the charge density. It's uniformly smeared out over that 4 pi r squared. All right. Which is kind of cool, right? Because the electric field right at that, right there, just right outside this is equal to that divided by epsilon naught. It's kind of cool. All right, so part B. Where was I? Oh man, I gotta get some more red markers. I'm running low on red markers. Weird. They're all over here. So for part B, my Gaussian sphere would be up in here somewhere, right? So let's say that's my sphere for part B. What's my charge enclosed then? The charge enclosed is Q. Is it reasonable to say that the flux is still the electric field times 4 pi r squared? Why or why not?
No. Wait, it would be.
Yeah, would it be? Why is that? The reason that that's reasonable is that...
Because it's the same amount. It's just going out further.
Right, because it's a sphere, the charge is uniformly distributed over the sphere, so there's a complete symmetry here, like the electric field here and the electric field there, it's the same. If instead of the inside having a sphere, it had like some kind of like lumpy pointy object, I couldn't say that. It would be, the electric field would be more close to the part of the object that had more charge. Like if your object has like a point on it, the electric charge will go to the point more than it will be, it gets pushed into the point effectively. There's a conversation we need to have in lecture about all this that I haven't neglected yet. It gives more nuance to why the electric field has to be 0 inside and how charge density works on a conductor. I haven't really had that conversation in lecture yet, so we will have that conversation. And by that I mean monologue in lecture. But anyway, I mean, I'm open to questions in lecture, it's just I'll get stomped. All right, so the symmetry of the problem allows me to write 4 pi r squared E, because the electric field is symmetrically outward from the inside. Okay, and so lo and behold, the usual thing. We get, Q over 4 pi epsilon naught r squared. That's the electric field in case B. And then, if you take a Gaussian sphere outside of both of these, out here, like so, right? What's the charge enclosed? Well, now you've got the charge in the middle, and you've got the charge on the insulator, right? So that's 2 times Q. And that's equal to 4 pi r squared E by the usual reasons, because it's symmetric, so the electric field has to be radially outward. So it's just the surface area with just 4 pi r squared times. And the r I'm talking about here, of course, is this, right? This is r. And so lo and behold, we get the electric field is 2Q divided by 4 pi epsilon naught r squared for r greater than 2r. It's probably a good thing for us to draw a graph of this and to talk about how this works, because there's some phenomena here that are interesting. So here's r, and let's look at r and 2r. Right? So what's the electric field look like? It's really, really boring here, right? Yeah, it's just 0, right? It's 0 down here. And then what happens at r? All of a sudden, it jumps all the way up to q over 4 pi epsilon naught r squared, big R squared, right? So it jumps up to here. I'll draw it like here, right? And then it levels down here till we get to 2r. I don't know, I guess, let's see, that should be a quarter, right? Because like I'm going from 1 over r squared to 1 over 2r parentheses squared, so it should be 25% of whatever that is, so like down to here. So it's an inverse square like that. And then past that, what happens?
It would go to double the height of the...
Right, double this, right? So like it doubled that right there, so it goes to like here. And then again, it inverse square law decreases like that. So there's a larger thing here to notice, which is that any place there's a discontinuity in your electric field, that's a place where charge is localized. See, there's charge localized at r, and there's charge localized at 2r. That's why there's a jump in the electric field. But the most commonplace example of this is just the Coulomb field itself, right? What's the graph of the Coulomb field? So let's put the charge, electric field equal to, kq over r squared r hat, right? This is just the plain old Coulomb field. That's it, right? What's the graph of the electric field magnitude? Well, it's like that, yeah? So it approaches infinity at 0. Why is that? Because there's a charge localized at the origin. So any place where there's a discontinuity in the magnitude, right? Or worse yet, an infinity in the magnitude, that speaks to there being a charge localized at that place. So you should expect this phenomenon in your electric field. If you're given a charge distribution and the charge is all like accumulating somewhere, there's got to be like a jump in the electric field. We mostly see this in these conducting sphere examples. The one place we didn't see this was when the charge wasn't localized, like that solid sphere example we did. The electric field started at 0 and it continuously increased up to the maximum value at the surface of the sphere, and then it like linearly decayed down from there. The other place where, an example wise, today we worked that problem with the solid cylinder. If you look at the formulas there, the electric field linearly increases from 0 at the center of the pipe to its like maximum value at the skin, and then it like decays off of that linear, well not linear, but like the reciprocal. All right. Was this it?
So if the conductor...
Oh, we can check our answers, right? Yeah.
If the conductor wasn't a conductor, then the first jump wouldn't have happened. It would slowly go up to that point and then slowly go back down.
Oh, right, yeah. If that was a solid insulator in the middle, then we would have had to actually like do the calculation.
Yeah.
It's not a bad idea. Like how would that